Hello, everyone. Hello. Does that work or can you hear me in the back? Or not quite? Yes? Yes, good. All right. So today it's my great pleasure to introduce Miles Stoudenmire. Miles is a world expert in tensor networks. We should hear more about it today, obviously. And he's also the lead developer of the iTensor software, which is an open source software where you can play with those things and discover by yourself. So I hope by the end of the talk, you get motivated to try yourself. Miles got his PhD from UC Santa Barbara, and he knows about cold Canadian winter because he was a research scientist at the Perimeter Institute. Then he did a short stay at UC Irvine, and he's now a research scientist at the Flatiron Institute in New York City in the Center for Computational Quantum Physics. All right, so really looking forward to your talk.
Thanks a lot, Valentin. Thanks for the invitation. It's really good to be here. Yeah, thanks so much for taking out the time to be here. I've really enjoyed my visit so far, catching up with people that I've met in earlier parts of my career, and it's been really fun. So looking forward to talking to more of you tomorrow as well. So I called my talk Decoding the Library of Babel. It's based on a short story I'll introduce in a little bit, but really the talk is about high-dimensional problems and solving them with tensor networks, which is only one of many ways to solve them, but it's one that I particularly enjoy, and I hope you'll get a feeling why by the end of the talk. I wanted just to start briefly by mentioning what is this, hold on a second, let's see. Okay, my clicker is not clicking, so, okay. I think, yeah, sometimes Zoom eats my mouse. Yeah, there. Okay, I think, yeah, okay, great, okay. Let's see, can I hide this? No, yes, there. Do you know, okay, great, let's see, great. Get this thing working. Yeah. There. Okay, perfect. Thank you. Okay, I was going to briefly introduce the Flatiron Institute. So there's us in New York City. That's the Flatiron building. That's not us. So we're just the institute. So we're down the street in this building. So Valentin, who used to work there with us too. So what is this institute? So that's more of a cross section if you want to see what's in the building. We're organized now into 5 centers plus a half center there. The idea is that all these centers you may notice have the word computational in the name. So what we're trying to do is we're trying to advance scientific research through computational methods, including data analysis, modeling, simulation. So this means things like showing how to do applications with computation, but also developing software, which is kind of unique. So we actually release a lot of open source, high quality software. Also, we work closely with mathematicians at our CCM center to really kind of like sharpen what we're doing and make it a lot more precise, much faster. Sometimes the math folks will come into our group and they'll look at something we're doing and they'll say, why are you doing it this way? Do it this way. And it'll be like literally 1,000 times faster than it was before. And we'll get more digits. So, you know, it's kind of fun working there. So just a little plug of what Flatiron is, so you know. So now within Flatiron and I'm in the Center for Computational Quantum Physics. That's this one here. We have a high dimensional problem. And I'll be kind of building up what I mean by that. But I would actually claim that high dimensional problems are not just in quantum physics. I'll probably highlight quantum physics the most, and this is the physics department after all. But really, they're everywhere in science, I claim, and even in industry. And often we don't see a high dimensional problem when we have one, but I'm hoping to help you be able to see them more easily when you spot them in the wild. So what's like a classic example of a high dimensional problem? So one that's close to my heart and is sort of closer to the type of work we do at our center would be studying a ferromagnet. And by a ferromagnet, I just mean something like an everyday fridge magnet, you know, just sticks to your fridge. So this is a magnet that can develop a net magnetization. And all I'm doing is I'm showing a 2D slice of this magnet. And so everywhere there's an arrow, that's supposed to be one of the atoms. And the atoms, for kind of complicated quantum reasons, behave individually like small bar magnets themselves. So they can either all point in the same direction, and then there's a net magnetization, or they might point in random directions, and then there won't be a net magnetization. And so if you model this magnet, including temperature, if you raise the temperature too high, all the magnetization goes away, and the spins are kind of flipping up and down randomly in a kind of probabilistic way. If you lower the temperature, they will all influence each other and align. and you'll get a net magnetization. It'll stick to your fridge again, right? So how do we model this? Or like, how do you think about modeling this? Well, the modeling starts by, anytime you have temperature, you're talking about probability. So you need to be able to work somehow or get information about the probability of spin configuration. So obviously then that's a map from the configurations to a number. It's what's the probability of all the spins being up? What's the probability of this pattern where the first spin is down, or the second atom, the second atom's down, the third atom's down. So there's some probabilities you can assign to each of these configurations. Okay, so that's pretty simple to understand. The problem is there's too many of them, right? So if you have n spins, there's two ways the first spin can be up or down. The second one can be in two states. The third one can be in two states. So that's 2 times 2 times 2, that's 2 to the n. Okay, so what? 2 to the n, right? Like that's not a big deal, but how bad can this get? So if you have 2 atoms, that's 4 states if you stored the whole probability list, like the whole probability array. But if you had 3 spins, that's 8. And by the time you get to 20 atoms, which is not very many atoms, right? That's 1,000,000. You go to 100 atoms, it's not a very large number of atoms. That's this number, 10 to the 30. And once you have 300 atoms, that number of configurations is greater than the estimated number of atoms in the entire visible universe, right? So anytime someone would come to us and say, I told this to some of the students earlier, like, you at Flatiron, the reason you're able to do this project is because you have a lot of computers. Your sponsors, bought a big computer cluster. That's not what we're doing at all. Like that wouldn't work at all, right? If we came with a problem this size and we said, let's just buy a few more computers and just hurl it at this problem, we wouldn't even make a dent, right? There's no way. So that's just to kind of tell you what I mean by high dimensional. But obviously people do model this system, and we'll talk later about how ways people do that. But first, what are some other examples where the same issue comes up, right? So there's actually quite a few examples throughout the sciences where this issue comes up. One that I really like, and this is a group out of Northwestern University in Chicago is pioneering this direction, is they're actually solving the classical rate reactions of chemistry. And I was surprised to realize that this is another high dimensional problem, because I would have just thought, use like, how hard can this be? You do this in high school and you do this balancing. If you remember this from high school, where you balance like this, 2 hydrogens and an oxygen are coming together and form a water and come back. So why would this be high dimensional? The reason is because that's just 3 kinds of atoms. So what if you have 10 kinds of molecules and you have free hydrogen atoms and you keep increasing the number of species? Very quickly, you have a probability distribution over all these many variables of all your different molecule species, binding and unbinding. And this is extremely important to like pharmaceutical companies that want to model how do chemical reactions occur at finite temperature if they want to develop a new drug, something like that. And closest to my heart is quantum physics. So we work with this thing called the many-body quantum wave function. And this is just manifestly a high-dimensional object because we have some kind of qubits, or they could be spins or electron positions. And similar to how we would store the probability, we store something a lot like that. The only difference is that our kind of probabilities can even be negative. We actually square them to get the probability. So these numbers we call amplitudes can be negative, they can be positive, they can be complex valued. So it's kind of even worse because we can have all those extra possibilities. And this is some kind of high-dimensional object that can describe many things, such as states of many particles, like gases of electrons, metals, but also it could describe the state of a quantum computer. So being able to work with this could be very important if people want to understand these expensive, complicated, or very technologically challenging quantum computers that are being built at different labs and companies in Canada and the US. How do we model these? Can we model them to make them better, to understand what they can do? We need to be able to work with this kind of high-dimensional object in some way or another. So now let's kind of think about how can we unify all these problems? Like, what makes them high-dimensional? Well, what makes them high-dimensional is just that somewhere in the middle of the problem, there's a function of many, many variables, right? So you have a function that eats some number of discrete variables. And later, if I have time, I'll talk about how you do continuous variables also. So the ferromagnet, it was the spin probability, these kind of high-dimensional rate reaction dynamics. It's the probability of configurations. Wave function is the wave function that takes all these qubits or spins. And the idea is that you can always, if you want, think of this as a giant tensor. So how do you think of it as a big tensor? I'm not going to get right now into like the details of what is a tensor, but I'm just going to define for now a tensor as a high-dimensional array and kind of forgo some of the formalities. But the idea is that the tensorized view of this function is to say, what if we just went ahead and plugged all 2 to the n inputs into this function and collected all the values that came out and just stored them in memory in a giant array? That's the tensor that I'm talking about. It's the evaluation of the entire function on all possible inputs, right? So that's kind of an impossible object, but you can imagine it, and you can think about this kind of tensorized version of F. And it turns out that is how tensor networks start, is you kind of think through that, then you sort of bypass that view, and we're going to come back to this later, how we actually break this thing down into a much more tractable form. Okay, but this tensor is really an imaginary object, right? As I mentioned earlier, just storing it, forget about computing with it, is an exponential problem. So you can never solve it by brute force. Another kind of little factoid would be, if you tried to store just a 100-dimensional tensor of index size 2, that would take as much memory in terms of RAM cards as the volume of the Earth. So there's another little factoid just to give you another feel for how bad this can be. Okay, so why is there any hope? Like, why would I even be giving a talk about tensors if you can never even store them, much less work with them? There has to be something else going on. And the reason we can do this is because all that high dimensionality I was talking about is an illusion. That's what the next part of the talk is going to be about, that really there's a hidden structure. We don't have to work with all tensors. We just have to work with like our tensors, or like tensors that come from nature or come from some kind of process that is tied to locality or structure, things like that. Okay, so there's a story that I use as kind of a framing device for this talk that I really like. I was curious how many people have ever read this story called The Library of Babel. Okay, we have a few fans in here. So Borges is this really influential author who wrote a lot of kind of sci-fi fantasy short stories, but they all have like a neat sort of twist in them, some kind of twist maybe about time or about space or memory or these kind of things. So they're really interesting stories. And I really like this one called The Library of Babel. And the story envisions, it kind of unfolds through a progression, but it envisions this library that's staffed by monks. And the monks will sort of live and work in different parts of the library. But the library is very big. And so sometimes there's sort of factions of monks that some live in one part and they have this philosophy about the library, and some live in another part. And over the course of the story, you come to realize, what is this library? It's actually an imaginary library that contains every possible 410-page book, where the book, all the pages of the book, is every combination of 25 characters that you can possibly have. So this is some amount of letters plus period, comma, and space. So that's what's in the library. So you start to imagine as the story unfolds, the narrator, which is one of the monks, starts to think about like how paradoxical this library is that he lives in. So what kind of books must be in this library? That kind of goes on and on and on. So one of the books in the library tells the entire history of the library, like when it was built, why it was built, what its ultimate purpose is for, how to find the book that's sort of the book of the truth of everything in the future. But then there's another book somewhere else in the library that contradicts this book at every point. It says, the library's always existed, nobody ever built it, you can't build a library this big, there's no purpose in this library, the books don't, so it just refutes everything in the first book. But both books must be in the library, right? So which book do you believe? Another book in the library has the entire theory unifying gravity and quantum mechanics, right? So if you could find this book, you would win a Nobel Prize immediately. You would just hold this book and you'd get the Nobel Prize. But there's another book proving that there can't be such a theory. And it says, this theory doesn't exist, here's why, and it refutes every single point. And then there's another book that's the same book, but just every other word is the word cat, right? So, and there's another book where it's dog, this kind of thing, right? And so part of the problem in the library is if you just go to a random bookshelf, most of the books are unreadable. Maybe it's in a different language that you can't read, but how do you know? You can't read that language, right? So maybe some of the books are nonsense. And so the monks kind of split into these factions where some monks believe most of the library is nonsense, but other monks think that many of the books are just in a forgotten language. And if only they could find another book that translates those, then they would have the key to the, So it starts to really kind of boggle your mind, like what's this library all about? But what's cool about this story is that it's really a story about high dimensions. It's telling you that high dimensions kind of can't really exist. Like there can't really be such a library because how could you really write all these books? So if we imagine these problems that are high dimensional, what we really need is like a card catalog for the library. We need some guide to the library that distinguishes which books are actually useful and have structure, and where if we learn the language the book is in, there's something in the book that means something from just random gibberish, right? And there has to be more random books than structured ones. That's the important thing. So how do we find a catalog that just takes us only to the useful books? And now I'm going to attempt a part of the talk that's a little risky because it's about a paper that I did not write, but it's a very technical paper, so bear with me, but I'll just have 2 slides on it. I think there's a really brilliant paper by David Poen, who sadly died in 2021, but he's an influential quantum information researcher here in Canada, in Sherbrooke. And I really like this paper because I feel like this paper kind of answers this question a bit about how do we understand the structure of the library for quantum states. So the idea in this paper is that they were considering states prepared by time evolution, right? You can prepare any state by a time evolution from some kind of putative state. So you'd start maybe with all qubits in the 0 state or all spins in the up state. Then you develop a Hamiltonian, any Hamiltonian you want, and the Hamiltonian is time dependent. So it has terms that are fixed in time, some that oscillate slowly, some that oscillate quickly. And what they argued through a series of mathematical proofs and arguments is that the fast oscillations make very slow changes to the states. They're so fast the state can't respond in any kind of reasonable time. So eventually, if you run the evolution long enough, the fast oscillations matter, but in any kind of finite depth evolution, they don't do very much. And so they kind of bounded this rigorously. And they argued that actually, it's only the smooth part that really appreciably matters if you time evolve for a reasonable, some kind of reasonable length of time. And it turns out that the rest of the space you can't reach. So it's there mathematically, but you can't reach it in any kind of reasonable amount of time or for any kind of Hamiltonian that's sort of not oscillating extremely, extremely quickly, something like this. So the idea is that most of the state space is actually an illusion. It's there mathematically, but you just can't physically like get there. You can't use it. So I kind of made a bad drawing of this, just a visualization of like, I was thinking of something kind of fractal like a plant, where you have a trunk and then branches and then smaller branches and then a leaf. And the idea is that in polynomial time, when you're preparing the quantum state, you can kind of get to a leaf. But then once you get into the leaf, you see the leaf is a smaller tree made out of smaller trees. And there's all these states. The reason I have this illustration is their argument is kind of like that. It's using like a idea about high dimensional space, that there's more points on the surface of a sphere than in the volume. One of these kind of counting high dimensional arguments. So the idea is that you kind of zoom in and you realize there's more and more points and you kind of can't reach them. So you need to do an exponentially long time to actually reach all the points in a ball nearby you. And it reminds me of the library. It's kind of like you can get to a shelf really fast, walk through the library, and you get to the shelf and maybe there's some books you can read at the bottom, but you look up and the shelf just keeps going and you would have to get a big ladder and keep climbing and climbing to get to all the books on that shelf. Okay, so what's the implication of that work? The idea is that even though the state space is very big, that's just an illusion, that the reachable states are a subset of the states we can really access, and they're an exponentially small subset. That's the key point. So that actually gives us hope in a funny way. Maybe we can identify that subset. Maybe we can sample that subset. Maybe we can parameterize that subset. And then it just raises the question of like, what are good sampling algorithms? What are good parameterizations to use? Another interesting point is that you'll see kind of a gap between communication about quantum computers from sort of in like the lay public. Like if you just go to like, Instagram Reels, you'll see these kind of influencer quantum computer accounts. Then you'll see the stuff written by like the true experts, and you'll see sometimes gaps in what they're saying. And one of the kind of more hypey things you'll see is people will say quantum computers are powerful because they operate in an exponentially large space. But if you actually go to the experts, they'll say, for example, Scott Aronson, I think will say this, where it's like, it's not really about that. It's about the algorithms carefully canceling plus and minus signs, and it's more about that. And I feel like this work by Pauline kind of makes that point in its own way, where it's saying it can't be that even a perfectly functioning quantum computer with a finite depth circuit can actually use the whole space. They actually have a circuit construction in their paper. So there has to be some other reason why quantum algorithms work. Okay. So I made the point about, could we sample this subset, this exponentially small subset of reachable states? Can we parameterize it? So earlier I mentioned, people are, high dimensional problems include magnets. They include rate reactions, but there are pharma companies that model those. We have been modeling magnets for decades and decades and decades, right? So how do we do it? There must be a way that we do it. And the answer is we have already plenty of methods. We have Monte Carlo methods, right? So especially if you have a classical problem, you can use Monte Carlo methods and you bypass high dimensions by saying, we're not going to try to store the whole vector of probabilities, the whole 2 to the n. We're just going to sample the big values. And the small values, they don't matter. It's like polling, right? You just call enough people, and once a pattern develops, you can be sure that if you kept calling more people, pretty much that's the pattern. So Monte Carlo, right? So if we have that, why isn't the problem solved? And this is the end of the talk. Well, the reason is, while it's very flexible and straightforward, so it's very flexible, you can throw Monte Carlo at just about any classical problem and many quantum problems. And it's dimension agnostic, highly parallelizable. There are some kind of well-known cons. I think any practitioner would agree that, for example, it really works if you have either positive distribution, it has to be positive, and then it also needs to be smooth. This may be a slightly overlooked point about Monte Carlo. If it's too oscillatory, even if it's positive, sampling can get really bad and kind of go wrong as well. And a really bad problem with it is that while you have a lot of parallelization, you get low precision results unless you collect a really truly large number of samples. So you'll kind of get the first 2 digits, but then to get the 3rd digit, you might have to wait an hour. To get the next digit, you might have to wait 4 hours. It can really get really slow. So we could maybe hope to do a little better. Neural networks are another way that people, I mentioned parameterizing high dimensions, right? So we could parameterize the subset. And so neural networks are doing that. And now these are really taking off, I think, for good reasons. Like we're seeing some incredible things in the many-body quantum space where I work happening with neural networks. So people are using these now to get incredible results for like 2D, strongly interacting correlated electron problems. So these are really great. But at the same time, all these methods are kind of in development. So they have some pros, they have some cons. So again, neural networks are very flexible. They're relatively easy to set up on a wide set of problems: high dimensional, low dimensional, continuum, lattice, broadly good accuracy. But the training can be expensive. You have to use gradient descent and variations thereof. Some of the theoretical guarantees are still currently a bit unclear. Do they give high precision on enough problems? So there's questions, These are all getting answered very fast. It's a very hot area, but just to say, still under progress, right? But other methods are still desirable. Like we could still want to have a larger set of methods to choose from. Many problems that we have are not fully always well addressed by the above methods. So in particular, when you have a many-body, many-particle quantum system or like quantum computer simulation, that's a time evolution of a quantum system. That's not so easily addressed with the previous two methods. Or in applied math, you have high precision integrals of oscillatory functions. In the rate reaction dynamics and classical master equations, you have dynamics. They use Monte Carlo all the time, but you might want to know about the long time approach to the steady state. Not just the steady state, but like how quickly do you approach it? Can you sample rare events, right? Things like this. So these are not so easily addressed. And we have linear algebra techniques. People that know applied math know that out of the whole math toolbox, linear algebra is like really the most powerful, the most fully developed area of applied math, or one of. And yet in high dimensional problems, often we kind of fall back to sampling or gradient descent. Why not linear algebra? Could we be using more linear algebra where you just directly construct the answer to something, right? Can we lift those powerful techniques into higher dimensional problems? How do we do that? Okay, so I would argue that tensor networks gives you a way to kind of address many of those things. Not everything, but it can bring some insight into these problems. So to kind of end the talk, I'll bring up three more specific challenges about high dimensions and show what tensor networks are and kind of how do they address each of these three challenges. So the challenges are the curse of dimensionality, challenge of the continuum, and the problem of loops. Okay, so we'll try to break the curse, we'll enumerate the continuum, and we'll believe our way through the problem of loops. Okay, so breaking the curse of dimensionality. So we saw that you think about the state space of high dimensional problems, like this function of probability of many spins or many rate reaction configurations or these things. You can always envision these as tensors. You can think about pre-evaluating all possible answers and store it and organize it into a tensor, so a high dimensional array. Okay, so for example, the quantum state of a system of spins. But as I said, large tensors are useless on their own. So let's go back through it. If every index has a dimension d, d could be 2, could be 3, 10, then the number of parameters inside this tensor is d to the n, exponential memory cost. That's what some people in applied math call the curse of dimensionality. In physics, I don't know if we have a name. Maybe we call it the many-body problem, this kind of thing. Okay, right? Now for matrices, which is a kind of tensor, it's like the 2D version of a tensor, two index. We have many, many ways of breaking this curse. Sparsity, sampling, but a really nice one is low rank factorization, right? So low rank factorization, and I don't have time to kind of develop all that too much, but the idea is if you have a matrix, and if the matrix has structure, it has patterns, like maybe some of the elements are the same, or maybe there's a lot of zeros, or maybe, we'll see one on the next slide. Then you can throw these very powerful tools at it, singular value decomposition, but also one called interpolative decomposition, rank revealing QR. There's this really rich toolbox. I'm curious how many people have heard of interpolative decomposition. I don't bet many hands. Okay, this one I really highly recommend learning about. It's like SVD, but more interpretable, but it works in the same cases. It's really, really cool. It tells you basically if the rank of a matrix is something 5, it tells you can actually pick 5 columns of the matrix and reconstruct the whole matrix from that. So this is very powerful. You can take a matrix that could be very, very big. Imagine this is 10,000 by 10,000, and you can, if there's a lot of structure, you can break it into 2 much, much skinnier matrices. And now you have a priori less memory you have to use up, but also fewer operations. So for example, let's say I now want to multiply m by a vector. I can first multiply the vector into b. That takes fewer operations because b is so skinny, it just has a few rows. Then I can take this tiny vector that comes out of b, multiply that into a, again, fewer operations. And it's like effectively I've multiplied this vector by this 10,000 by 10,000 matrix, but with way less work on the computer, right? So if the matrix has a structure, I can save memory and save time, use less electricity, all this kind of thing, right? So here's just a concrete example of what I mean by a low rank factorization, right? You could come to this matrix here and say, that looks random, I don't see any patterns, but you you stare at a little bit more and you notice, okay, some of the numbers are the same. I see 0.16 twice. Okay, this vector and that vector kind of go up and down and up and down. And sure enough, this is a rank 2 matrix. It means that all the columns are linear combination of just 2 columns. And the SVD will automatically discover this for you. So you do an SVD, that gives you 3 matrices, you multiply 1 over into B, and then it reveals the structure. It tells you that actually it's just 2 skinny matrices multiplied together. So the point just being that we have automated deterministic methods that can reveal structure in tensors, but they are really mainly developed for matrices. So can we use this in high dimensions, or are we stuck only using these for matrices? Well, it turns out there's a very clever way to just shoot this up into high dimensions, and that's called tensor networks. And you can think of it as just taking SVD and iterating it recursively, or kind of lifting it to high dimensions. Okay, so here's how that works. So let's say we have a big tensor. What we can do is we can actually imagine it as a matrix in the sense that we can just declare this index here to be the row, and all these indices, we can just group them. Like if you've ever used NumPy, you can call reshape and say reshape, and it'll just view this data as a very, very lopsided, very, very rectangular 2 by 2 to the n minus 1 matrix. And you can call an SVD on it, and the SVD will run, and then it'll reveal some rank. And if the data is random, the rank will be terrible. It'll just be like the maximum rank. But if there's structure, like if your probabilities model a ferromagnet, or if your wave function comes from a short time evolution, something like this, the rank will be really small. It'll come down. So you can reveal this rank, gather these factors, do low rank decomposition. Then you can just say thank you to this small tensor that come off, kind of detach that, and then do an SVD on the remainder that's left over, reveal a second rank. And you keep reshaping and kind of folding the data into matrices, calling SVDs, and going across. And the idea is that you're kind of zipping and unzipping structure in a tensor like this. So this is a very powerful technique you can do. Okay. Now, sometimes this works, sometimes it doesn't. It really depends. As I said, if the data in the tensor is random, this just goes terrible. The ranks grow to the middle to an exponential size, and you're done. But if the data is patterns, like for example, if the tensor just all the numbers were the number 1, this would work perfectly. All the ranks would just be 1. So you can get a massive gain in the best case. If all the ranks are small, especially if they're just flat, if they don't grow, you can get a really good compression. And just as a terminology thing, in tensor network parlance, we call these ranks bond dimensions, but in the math literature, they call them ranks. Okay. So sometimes you hear tensor network people say bond dimension. How much do we gain? Let's just do some counting. So say, just for convenience, all the ranks or bond dimension were all the same. They usually vary, but let's just say they're the same. How many tensors are there? There's n of these tensors. They have external index size d and internal index size or bond dimension r. So we just do some counting. There's d r squared elements in each tensor, except the ones at the end, but don't worry about that. There's n tensors, so that's n times d r squared parameters. And the original tensor that this models had d to the n parameters nominally, right? So you see this is an exponential improvement. This is an exponential speed up, exponential compression. So we had the n and the exponent over here, and then somehow by repeating this SVD, it's almost like we are able to take the log of the number of parameters and pull the n all the way in front in the best case. And in fact, if it's translation invariant problem, we can even get rid of the n sometimes. So you can just get this enormous gain of exponential gain of power on these problems, right? So even though these problems are exponentially hard, the point being is that we can also get exponential speed ups on these problems in some cases. So there's a lot we can do. This format that I'm kind of laying out here is known as a matrix product state tensor network or tensor train. So if you ever run across those terms, tensor train, matrix product state, that's the same. It just one has a math pedigree, one has a physics pedigree, but it's really the same idea. And this is kind of a seminal example of what's called a tensor network. And really all the tensor network is just, it's sort of like a neural network, except there's no nonlinearities, there's no neurons. It's just made of tensors contracted together, and it represents some big tensor that we never want to have. We can't store the big tensor, just like you can't store all the outputs of a neural network, but we can break a big tensor into small tensors and store those. Okay. And then this realizes that thing I said earlier about the library of Babel, where we want some kind of card catalog, like we want some kind of map or some kind of way to parameterize a useful space. And the claim is that these tensor networks are one way to do that. That if you think of the parameters in these tensors, these are some latent parameters that if you change all these parameters, you sweep out a small, low complexity or low entanglement, low quantum entanglement manifold in the full quantum state space. And then you hope it's a useful manifold. Maybe it's not for your problem, but for many problems it turns out to be. And I wanted to make a little sidebar to say I've been drawing these pictures, and a lot of you may just think these are figures. But actually, the whole time I've been showing you math equations. So these are a very precise notation called Penrose diagram notation. How many people know that notation, Penrose diagrams, tensor diagrams. Okay, some of you do, but many of you don't. Okay, great. So I have a little tutorial just for a few slides that I'll just kind of torture you with for a second. So I really like this notation. I think it can even be like a good way to teach people linear algebra, like even just what's a transpose, how does a trace of a matrix work? So the way this notation works is that you start from objects in linear algebra, tensors, vectors, matrices, and you take the shape, or you take the letter and you replace it by a shape. So this shape represents V, this green shape is M, and the indices become lines sticking out of the shape. And the nice thing about it is that at first you put the names, but later as you get more used to it, you just drop the names. Because the names, many of them don't matter, they're summed over, you can put them back, they're clear from context. So this is a tensor diagram for a vector, 1 line, matrix, 2 lines, third order tensor, 3 lines. The other nice thing about it too is that you'll see in some literature, people will try to draw like a order 5 or 5 index tensor, and they'll draw it as like a 3D cube next to another one. Like they'll try to visualize in this high dimensional space, and it's very good for teaching. However, when you're doing calculations, you can't like draw a tensor in 3D or 4D, right? So this gives you a really nice way to draw like a 3D object. You just 3 lines coming out, okay. And the other part of the notation, it's actually very closely related to quantum circuit notation. It's kind of like a relaxed version of quantum circuit notation, is that when you join the wires, it implies a sum. So it's kind of like Einstein notation where you repeated indices are summed, except here, we don't even put the letters. So it's kind of like one click like past Einstein notation. So this is just a rigorous notation on the left for, you see there's an object with 2 indices connected on one wire to an object with 1 index. So the 1 index must be a vector, that's a matrix, and it's kind of like a visual theorem or visual proof that a matrix times a vector is another vector, because you can just see, well, there's 1 wire left over, so whatever this thing is, the result must be a vector because I see 1 wire sticking out, that kind of thing. And that's the traditional notation for the thing on the left. So you see, we didn't have to write the names. You don't have to kind of go index hunting, so it's kind of nice. All right, so that's just a 1-slide refresher on tensor diagrams. So you can see why I had that, because now when I'm showing you these diagrams, you see these are actually precise mathematical constructions. So I showed you the tensor network called the MPS, matrix product state tensor train. There's also other varieties. So when we do kind of 1D problems with 1D correlation patterns, we use MPS. When we do problems in 2D or 3D, we use appropriate generalizations of these. We call them PEPs for kind of bizarre historical reasons, but 2D tensor network is probably a better name. And there's other kinds too. There's kinds that deal with multi-scale systems, 3D systems, all kinds. In some ways, you can think of these as being similar to neural networks. Like one of the main operations you do with a neural network is you evaluate it, right? You send inputs into the input neurons. These trickle through the weight layers, through the hidden neurons, and then output a number. If it's scalar valued neural network, you can use a tensor network that way. So you can set all the external legs to some specified value. And what you're doing is you're accessing an element of the original 2 to the n array or tensor, but you're accessing it bit by trading off storage for computation. So you're saying, let me access the 1, 2, 1, 1, 2, 1, 2 element. How do you do that? So when you set these indices, it's like I'm slicing out the 1 slice of this tensor, the 2 of that one, the 1 of that one. So those legs are gone. So what's left over are these objects, which you can see are, that's a vector, that's a matrix, a matrix, a matrix. So it's a chain of matrix contractions. That's why we call it a matrix product state. And then you can do efficiently this computation. You just go vector matrix, get another vector, vector matrix, get another vector. You just keep kind of contracting, contracting, contracting. So in a very cheap polynomial time, you contract until you get a number, and now you've retrieved the element of this 2 to the n. So it's kind of like we've gone into the library and we've been able to grab a page off of one of these books, something like that. But we never had to hold all the data, right? We never had to hold the 2 to the n. We can just retrieve it on demand. So you can actually use these like neural networks. If you wanted, you can now do back propagation, put them in PyTorch, train them, use them for machine learning. People have been doing all these things. It works pretty well. But that's actually kind of the point of this part of the talk, is to say, what's really interesting about these is not the architecture, it's not the representational power, it's actually the algorithms. It's that we don't have to use them that way. We can, but we have all these other things we can do with them that really use linear algebra and are kind of quite interesting how they work. So the key difference is that we have novel algorithms for these tensor networks. They're all built on linear algebra and tensor contractions. So for example, if we want to simulate a quantum computer is made of gates, and we can manifest a 2-qubit gate as a tensor. You can always like evaluate all the elements as a tensor, and we can absorb that tensor into a tensor network just by placing it on the relevant qubits, pulling out those tensors, contract, do a low rank matrix factorization to reveal structure, and put it back. So you put it back, and then you bring the next gate, that touches some other qubits, you contract. This is actually code you can write. This is just like a page of code that you can write. You do an SVD or some low rank, put it back, and now you have like a simulator for a quantum computer on your laptop that maybe will crash after a while. Like if you try to simulate some kind of quantum advantage circuit that's exponentially hard, you won't get very far, but you can always do a few gates and do some useful science with this. So this is already kind of an interesting one. And what's neat is that because this algorithm involves low rank factorizations, it'll discover structure automatically. So it's kind of like a neural network that's automatically able to adjust the number of weights and neurons on the fly. So if you give it a circuit that happens to only evolve to a very trivial state, these what we call bond dimensions or ranks, they won't grow. They'll just plateau or something. But if you try to simulate toward a very high entangled complex quantum state, they'll grow, and then basically the code will sort of throw up a flag and say, I'm out of resources, stop. But you've learned something about the physics of your problem. Okay. You can do many other things. You can perfect sample these. So once you've prepared a state in this form, you can collect a sample. The idea is that you basically form a density matrix, look at the diagonal, it tells you a probability of 0 or 1. You roll a dice, you pick one, like say maybe I pick 1, and then you project the state, and then you collect the remainder of the state, form another density matrix, look at the diagonal, and so on and so on. And what's neat about this one is that there's no Markov chain, there's no autocorrelation effects. So you don't really have to do Monte Carlo, you just collect a sample, and that sample is guaranteed to be a true draw of the distribution modeled by the network. So the point is that we have this kind of cornucopia of different things we can do. We can apply gates, we can collapse, so there we have an entire sort of mini quantum computer in a box, if you want. Now, the seminal algorithm for tensor networks is called DMRG. The name is kind of historical, density matrix renormalization group, but people debate if it's a good name, But what it really should be called is like matrix product state eigenvector finding algorithm. So you have a big eigenvector, it's not a good name either, but you have a big problem. It's like a 2 to the n by 2 to the n matrix, and you just want to find its dominant or sort of largest eigenvector. So we actually have a really interesting way of doing that. And I'm partly mentioning this one because I have a couple movies, so I thought it'd be fun to show. So let's say we want to find this eigenvector, but how do we find this eigenvector if we never can store the answer, right? We can just guess that the answer forms this tensor network and try to find it. So the way this works, and I won't have time to go into the details, and probably a lot of you don't want to see the details, but we actually can take a partial guess for the answer and use it to project the problem. So we can take this huge matrix and kind of shadow it down into low dimensions and get a projected form of the operator. And now this is something we can solve, but I wanted to make the point that people will call this like a variational algorithm, and they'll think we're doing something like gradient descent, but we're actually using very fast methods like length shows, which can converge exponentially quickly, and running basically like a mini exact diagonalization problem in this reduced space, get the answer, plug it back in, move on, and we can kind of sweep back and forth over these tensors and optimize them one by one by one. So here's an example of how this looks, and this is basically like real speed, assuming my computer is going to run at the proper speed with Zoom and everything. Movie of us solving for an eigenvector of one of these quantum Hamiltonian problems. So these eigenvectors represent kind of a steady state, equilibrium state, where if you cool a system, this is a particular kind of 1D magnet, quantum magnet, if you cool it, it enters into this equilibrium state. And what I've done is I've preloaded the answer as a reference, and I'm just showing you the error of every bond of this 1D problem and how quickly it converges. So this is what it looks like. So there's one pass of DMRG, second pass, and you see it's just order of magnitude by order of magnitude converging. And this is basically real time on a laptop. That's about how long the calculation actually takes. So that's for a problem where the first eigenvalue is really well separated from the second one, so it's more easy. If I switch the problem slightly to one where there's no spacing between these eigenvalues, it has to work a little harder. So you see it's still doing a pretty good job, but it's what's called a critical system, so it has to really work. So you can almost kind of see physics in how it converges. I just like to kind of think about, maybe there's some emergent physics even in how this algorithm looks to converge. Okay, so that's just kind of what it looks like. But that's, again, kind of real time, and you can see the energy in the corner going down, and after a while, it's really just putting on kind of digit after digit after digit. Okay, another fun one from this literature is called tensor cross interpolation. I wanted to mention this because often when you hear about machine learning, people will kind of conflate machine learning with neural networks these days, and for good reason, right? Like many of us have used these LLMs, they're incredible. I had one write an article just the other day for a page I maintain, so they're awesome. But I think for the sciences especially, we need really like high precision machine learning also for certain tasks. Because some tasks we can't just kind of get away with text. We need like the answer, and we need it to like 8 digits or something, right? To really predict something important. And we also need interpretability. We need to be able to know, why did these numbers end up the way they are? Why is it this many numbers in the answer and not this other number? And this algorithm called tensor cross interpolation, which actually now is about, I think, 15 years old, really gives you all this. It's been around a while, but to our shame, people in physics had kind of ignored it. We didn't know about it. It was developed in like a Russian mathematical school, and we just didn't understand it. And we met the authors, and they taught it to us just in the last 3 or 4 years. And we're kind of blown away by this algorithm. It's really fun. So to give you a flavor of it, what it does is it performs a kind of machine learning called active learning, where it actually not only learns, but it also figures out what data it needs on the fly. And it does it in the form of a tensor network or a tensor train. So you have a function that's very high dimensional, and it goes in and starts sampling the function, and then it interpolates between the values that it sampled, and then it backtests. It says, how good is my interpolation? Well, I can find out by putting another point in between and measuring the error. And it does this in a really smart way where it's kind of triangulating high dimensional space, building up a tensor network, testing its hypothesis, testing. Plus the SVDs, what they can do is if too many interpolation points get close together, it can prune them out. It'll kick out ones that are too close together and kind of spread them out in a really nice way. It's very cool. So I made a movie just to give you a flavor. So this is a pretty challenging 1D function. It's the sum of 40 Gaussians of random positions, random heights, and random width. So you can see there's broad features, narrow features. There's a sharp discontinuity there that I just put in by hand. And the idea is we want to be able to do something like take an integral of this function, and get the answer to like many digits. But we have to be able to load the function. How do we get it into a tensor network? And this tensor cross can do this. So here's a movie of 2 passes of it running just to show what this looks like. You can see it's just interpolating everything. So actually, you'll see there's some errors because I'm only running 2 passes. Normally, we do like 5 passes, and then everything will be accurate to like 10 to the minus 6, 10 to the minus 7. But that's the movie of it running, building the interpolation. But what's neat about it, you may say, okay, but I can interpolate this one by hand, just draw the lines. The difference is you can do this in any number of dimensions. So you can do this in like 10 dimensions, 30 dimensions. So researchers at CCQ, who I work with, tried this on a very nice problem. This is this paper from 2022 that's relevant for physics. It could be relevant even for high energy physics. They used it for quantum dot mesoscopic physics of summing Feynman diagrams, right? So Feynman diagrams are basically values of a function of many variables. The many variables are like where the diagrams touch. You can think of those as the space-time points. And then there's a number, that's the diagram. That's the output of a function. But if you think about it, the sum of all diagrams is a function. It's just a function of space-time points to those numbers. So you can think all diagrams of order 10 is a function of 10 variables. All Feynman diagrams of order 30 is a function of 30 variables. What if the function is actually pretty nice, even though there's a lot of diagrams? So they said, why don't we just learn this function in this way? So they pointed this algorithm at these functions, and every time the algorithm would ask for a value, they would run a Feynman diagram on the computer and give it the answer. And it would just query Feynman diagrams, and they would feed it the answer. And it actually was able to learn all orders of Feynman diagrams up to something like order 30. And they could have kept going, except their code to evaluate was a little too slow. I mean, it's a tough problem. It's a very complicated many-body problem. But the result is that they could pre-model in time the entire dynamics of an interacting quantum dot interacting with a lead of electrons. And what I mean by pre-compute is that you compute sort of the skeleton of the answer, and then someone can bring you the drive. They can say, I'm going to externally drive this quantum dot this way. And then within like a second on the computer, you can compute all the properties in time. And then if you say, now I'm going to drive it that way, they can recombine their data and compute the properties again in like a second on the computer. So it's like you're actually getting an answer that tells you all possible answers about this dot, all just on kind of conventional computers. So very nice project by those folks. Another fun one is there's a group in this Journal of Robotics Research that see what I mean about not using the tensor diagram. So there's some tensors that are modeled in 3D. They use the same interpolation algorithm to actually control a robot arm. So this is also what I mean about high dimensional problems really are everywhere. So in robotics, they're running this kind of funny tensor network interpolation algorithm to learn the kind of cost function landscape of a robot arm. Is it close to its objective? Is it far? Minimize the motion, and actually picked item off the shelf. And a really nice thing about this literature is that they have actual photographs, like time-lapse movies in their papers where you can see time-lapse of the robot moving off and on the shelf and all this. So one thing I think it's like fun to think about is that even though these tools are being developed in one field that's a very tough field, like quantum many-body physics, maybe they're already really good because those are like really hard problems. Maybe there's other problems that we can just be applying them to and getting great results right away. Okay, I'm going to skip this section. I figured I probably had too many slides. It's basically just about how do you input continuous variables. I wanted to highlight the one other application that I think is cool. Those of you who do physics, many-body physics, is that because of this ability to harness high-dimensional problems, there's a really nice project just published last year, December 2025, where some researchers realized you can use these to store non-interacting fermion states, Slater determinants. Like, so you'd think, well, isn't that trivial? If you know about non-interacting electron physics, those are like polynomially efficient states to store. However, what if you have 1 billion electrons? Now can you store it, right? And it turns out you can if you use this kind of compression that I mentioned earlier. So they found a way to map non-interacting physics, but on 1 billion sites into these tensor networks and write all the equations in this form. And the upshot is they can now run Hartree-Fock calculations for Moiré systems where you have these very long scale modulations in space of the background potential up to 1 billion unit cell and solve these accurately on just like a conventional computer. So I would encourage all of you to take a look at this work. This is really kind of nice ideas that are coming out. And let me just end by talking about the problem of loops. So there's this really great team we have at Flatiron that I call the believers, and you'll see why. I'll just kind of flash through this part. So there's a lot of claims that quantum dynamics can be hard for classical approaches. For people using conventional computers, simulating dynamics in time can be very hard. And sometimes it's said that it's always hard. And it's definitely sometimes hard. But is it really always hard, And why is it thought to be a hard problem? So if you use techniques like quantum Monte Carlo, if those of you who know, it has this thing called the sign problem, that can really make it hard. For these tensor networks that I've talked about, you have growth of complexity of the state in time. So generically, if you just modify a state, run quantum mechanics forward in time, these ranks I showed earlier grow and grow and grow, and your computer blows up pretty fast, okay? So what's also behind these claims is that we try tensor networks, but we try them in a bad way. Often we want to use that one-dimensional network I showed you earlier, and we just zigzag it through 2D. Why should that work? It kind of works, but it's a bit primitive. It's because when we use these 2D tensor networks, the algorithms we haven't been very good in the past, basically. So we knew about these networks, we just didn't have good algorithms to work with them. But it turns out the answer to what to do, or one of the newer answers what to do, actually had already been figured out in the 1930s. So I was saying we just have to believe that new algorithms will come along. And I'm just making like a bad pun because there's this idea called belief propagation. It's a very old algorithm. Tensor networks a much newer idea. And if you combine these together, you get very affordable dynamics of quantum systems in time in 2D and in 3D. And so belief propagation is basically this way that you can take your tensor network in 2D or 3D. You can kind of cut it in this way that's sort of a principled way, like putting mean fields around your tensors. Then you can apply a quantum circuit, run your thing in time, and do this even in 2D and in 3D, and even to surprisingly long times. So just to mention this belief propagation algorithm, it goes back as far back to 1935 with Hans Bethe, was updated in 1982 by Judea Pearl in the computer science community, and has been used heavily in spin glass physics. And basically, there's like a quantum analog of this algorithm. It's very simple. You just take the kind of stat-mech models that they studied in this seminal literature, and you just view a doubled quantum state, Bra, Ket, stacked together as a stat-mech problem. You just take a top-down view, and then you just run all their algorithms. And the bottom line is these algorithms are really cheap, and we can kind of deal with the fact that these 2D tensor network have loops by doing this belief propagation, where, let me just kind of flash it up here. We basically guess ways to cut the network apart into little patches. We remove these little vectors that we attach to the legs. We sum the other ones through. We send the vectors over to their neighbor. We do this over and over again. The quantum version of this is that really there's 2 layers, Bra and Ket. We're really sending matrices back and forth. Then we can apply a gate, evolve in time, and simulate 2D and 3D systems in time. And we've been able to do this in 3D and actually compare it to a D-wave quantum annealer system and get competitive results for all sort of annealing protocols where we can actually, they can run their hardware, their simulator, a D-wave, through slow adiabatic evolutions, through fast ones. And by doing this kind of belief propagation method in 3D, and now there are these new technologies on top called loop corrections where we can correct away from this kind of simple limit, we can be competitive with this kind of hardware, and we can see interesting physics like collapses of, universal collapses of correlation functions of time-evolving 3D quantum systems. This is called Kibble-Zurich physics. You can kind of do it slowly, do it faster, faster, faster evolution of your state, calculate correlation functions in space, rescale them in a certain way and they'll all collapse. And we can do all this interesting physics, all on kind of like laptop level calculations and things. So, so I'll just end there and say, we have a lot of structures that we're using now to make these classical calculations work. I mentioned this organizing principle of tensor networks, but there's many other principles we can use: high dimensionality, large loop structures, Gaussianity. So we're kind of thinking a lot about structure in what we're doing. And I'll just kind of leave up my thoughts in future directions slide and say, these tensor network methods are really kind of helping us in a more refined way understand the boundary between not just a problem is hard because of 2 to the n, that's not really the problem. The problem is that we need to carve the space up better into hard and easy problems and understand how to kind of move through the easy problems and kind of sip from the hard problems, right? And these tensor networks bring radically new algorithms. I wanted to just mention that point to say that very often I feel like the vision you hear from like the tech world, like if you listen to like some of these AI CEOs in the US, they'll say, the future is using more electricity as much as we can. We just need a lot of capital and we need to burn down forests and just, cover a state. I heard someone in New York the other day at dinner say, we need to turn the state of Iowa into a big computer. Like I literally heard this, okay, maybe Americans want to do this. Sorry for my country, but I would just say in general, I'm not like that. And I think what we need to do is we need to say, maybe we could use the computers we have better. And some of these ideas I mentioned could be a way to do that. So we have new tools to learn tensors from data, to map high dimensional functions, do dynamics. And so I think there's great science to do with all this. So thank you. Mm-hmm.
It's a fascinating talk. So one thing that I'm really interested in is the fact that, so you gave an example of data that looks like it's exponentially complicated, but actually it's not. And maybe one of the miracles of machine learning is the reason that it works so well is that natural data seems to have this structure that is actually secretly low dimensional.
Right.
But the really cool thing about your data set problem is that you have this completely complementary approach that doesn't require machine learning. But then can you then turn that around and say, okay, then if you train a neural network on, say, data sampled from some time dependent Hamiltonian or whatever, then that would let you look inside a little bit and try to get some, kind of insight on the interpretability based on the fact you could solve the problem from a different direction.
Yeah, it's a nice idea. I mean, I think we should do that very much. Like we could use this, people to some degree, they'll use these tools that I highlighted as a way to generate data. Like the tools, you might have seen, this one network I featured the most has a 1D structure, like a chain. That's the one where we have the most algorithms. Now we have good algorithms for the other ones too. But that's the one that we've had great algorithms for decades. So they'll use it as a way to generate very faithful, high precision data for hard problems, then feed it into a neural network and say, can we, for example, use the neural network to predict answers fast on all these without having to rerun this sort of called like high level calculation? But it's a real interesting conversation now because, I mentioned that cross interpolation thing. These tensor networks can also function as a first class machine learning method themselves. So, but then, an obvious question would be like, if that's really true, why don't we throw out LLMs and use these? Well, okay, they're not as good at that kind of machine learning. But it's interesting because it's like, but they seem really good at like I talked about summing all Feynman diagrams, right? That seems really hard. So I think we need to figure out that there's machine learning and there's machine learning. There might be like this kind of machine learning the neural networks are good at, and another kind that these are good at. And I kind of think it's like if you can cast your problem as a smooth function or some function that has like you find the right basis, then this can really do better than neural networks. But it's very problem dependent. Mm-hmm.
I was just wondering, in general, how could the size of the bond dimension help you to interpret what kind of quantum phase of the system you're looking at?
I like that question because it's the size, but it's even more. So there's actually these tensor networks. I don't think it's too fancy to say they're literally gauge theories, these tensor networks. There's a huge gauge symmetry inside the bond, meaning that on every bond, I can put a matrix to the left and the inverse of that matrix to the right. And it doesn't change the visible state, like the physical state. And so you can actually really play with this freedom on the bonds by putting in pairs of matrices or finding gauges. And you can also cut the bonds, kind of cut them open and look at the structure of the state relative to the bond space. And there's been some really nice work that shows if the state is realizing some kind of like exotic order, like these things like topological orders, there's this whole counting that can go on in the bond space that has to do with these fancy field theories, conformal field theories that can actually fingerprint this topological order. And there's many other such examples. So I think a nice question would be, that's worked in physics. what if we use tensor networks in, rate reaction dynamics? Are there fingerprints in the bond space too of things? Are there interpretable structures? Mm-hmm. Yeah.
So this reminds me a lot of compressive sensing and image processing, optics, and about how to store large images in a very efficient way. Have people looked in the connection between compressive sensing and tensor networks?
Some. I think one thing is that a lot of those, some of those ideas are doing a low rank in the other direction. So they might be saying you have like a matrix, like a high dimensional matrix for us could look like this. And many of those are thinking, what if we decompose it this way? And many matrices are low rank in that direction. But the tensor network way, I mean, this is a tensor network, of course, but the one we do is more like this direction. So we chop it up that way. And sometimes what I mean is there's low rank and low rank and low rank. There might be multi-low rank depending on where you cut. And some problems may be low rank in one way, and it's kind of like cut here, cut there, So there's really a lot of low rank formats that have only recently been started to be explored. And so that's one reason. But I think, in fact, we probably need to go in that toolbox more. There's a whole toolbox of like blocked linear algebra, things like Schur complements and Sherman, Morrison, Woodbury, and the stuff that I think we're barely scratching on. We need to use more. So.
Would you go back to the slides for a bit? Because I want to see something.
Which one?
Just keep going. I forgot what slide number it was.
Sure. I was skipping on this part, but maybe in the middle?
Yeah, around the middle.
Okay. Here, say. Could you describe the slide?
Was the launch shows. That's
okay, yeah. Right. I was giving just a flavor of what's going on inside our eigenvector algorithm. Yeah.
Okay. What was my question? So you said something about the DMRG algorithm. I kind of forgot what it was because I was
the name is not very helpful, but what this algorithm does is it's trying to solve a giant 2 to the n by 2 to the n eigenvalue problem. I didn't really say, but the matrix, of course, we can't store that either. We have to store that in pieces. But usually this matrix is a sum of products of very small matrices, so we can store those. But the vector a priori is a dense 2 to the n vector. And so how would we even if someone could give us the answer, how would we even store it? So we just posit that maybe it's factorizable this way. Okay. Then we say, let's look for the factors one by one. Like, let's kind of guess these factors and maybe try to optimize that one, then freeze that one and optimize that one. And so we do this thing called sweeping where we go back and forth. And at each configuration, we pick one factor that's unfrozen, and then we like solve a small linear algebra problem. And one point there is that shoots us to the answer very fast. We're not just kind of tiptoeing to the answer. We're kind of like zooming to the answer in these giant steps.
Okay.
So it's very, very fast.
So going really fast by like kind of removing the unwanted information and just.
Yeah, it's kind of like if you have a high dimensional space and you pick an axis, we can basically just jump to the answer almost on that axis. Then we can switch to another axis and jump, Okay. So the only thing holding us back is that in the other frozen axes, we're on the wrong plane. If we were on the right plane, we would just get the answer immediately. But so we kind of take it down plane by plane, and just each plane we jump to the answer, jump to the answer, jump to the answer. So the only thing that's slowing us down is the other planes are wrong. But once we get them all aligned, we're done.
Okay.
So,
then
yeah.
I was thinking about Lanch's algorithm is basically, it can take like a really big matrix, convolution matrix, I think, and basically can convert to a tridiagonal matrix, and then from there can take its extreme eigenpairs and then use that. Yeah. So I was thinking, what's the difference between this Lanch's algorithm and the algorithm you described before?
Oh, what's the difference? Yeah. So, right. So Lanchos, though, is a bit more agnostic about your problem. This one is only working when you make certain assumptions about the answer. Lanchos is more just saying, it's more of a black box. So you say, I can multiply my matrix times any vector. That's all you need. But that's also kind of pessimistic because you have to be able to multiply by any vector. Here we're saying the vector has to have a special structure, and we're using that structure. So I think that's another theme about high dimensional problems, is that we're very often used to in the past when you learn algorithms, like, you go on Wikipedia and you read about an algorithm, sorting algorithm, you'd say, what is like the complexity of the algorithm, right? But anytime you say the complexity, that's like as if there's one complexity. But it's like, what are you sorting though? if it's already sorted, there's the complex, you don't have to do anything, right? So this is kind of the theme, I think, with high dimensional problems, is that you start to realize that these algorithms, their runtime is much more problem dependent. There's not just like a complexity of it. It's very like case by case by case. Yeah.
Okay, because what I was thinking is for, implicit,
should.
we started long.
Just, probably have to let someone else ask those. Yeah,
Yeah,
let's chat after.
So I guess we'll take one more question.
Yeah.
You're welcome to continue talking to the speaker in the lounge.
Thanks for the questions, though.
Thanks for the talk. So you mentioned something about when you're building your matrix product states, you're cutting in a certain order and then going back and forth.
Right.
And then you also mentioned the answer to a previous question that you can cut along different directions. And I've also heard that in tensor contractions, there's questions of what order you're going to contract in.
Yeah.
So my question is, how difficult is it? Is it more of like an art of a science to decide all these like orders that you're doing things and where you're cutting for a specific
there's actually a whole science there. It's a good question. So historically, the way we had worked in our kind of corner of our field is that we would kind of handcraft the order in our code. We would say, put these together, factorize them now. We'd kind of write all that ourselves. And that's fine for simpler algorithms. But it turns out there's really nice kind of heuristics you can do where someone gives you a really complicated graph of tensors and says, contract these. Even if there's an efficient way to do it, there's so many ways to, how do you know what the efficient one is? And you can basically work on this in different levels. You can say, I don't need to know what the data is. I just need to know the size of the bonds. And you can do all these kind of search heuristics very fast on a computer. Even though it's an NP hard problem, you can still find like reasonable solutions that might be, suboptimal, but very good. And it'll actually tell you the order to do. So we're using this more and more in our code where we just turn it over to the computer and say, here's a bunch of tensors, tell us the order. And what's nice about that is sometimes our bonds adapt during the code. So the code's running, this bond will be bigger, this one's smaller, and it'll switch. And the code can switch the strategy dynamically while the code is running and do the contraction the other way.
Could you maybe mention the name of some of these techniques?
Oh, there's a bunch of them, but let's see. The simplest one is just called greedy. So you literally just pick a starting tensor and say, what next contraction would be the cheapest one? But then there's a bunch of hyper greedy, metis, blah, 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 blah. There's like a whole zoo. So there's some really good papers actually out of Sherbrooke about this. Stefanos Kortis at Sherbrooke. Yeah.
Okay, thank you.
Mhm.
All right, I guess let's thank the speaker again.
Thank you.